David Smith here with one more Flip Classroom Math video. 3 tips before we start. You could turn on the captions and watch my words go by on the screen if that helps. You could also speed up the playback if you can get through the video faster and still comprehend. Lastly, you could pause video at any time and catch up on your notes. Today's lesson is intended to provide you with an introduction to the binomial distribution. Now, this is a way that we're going to do probability, but it's kind of complex. But it needs to be because the situations we're trying to analyze are also complex. For example, let's say you flip a coin 10 times. What's the probability that you get exactly 2 heads in that passage of 10 flips? And you might be able to figure that out with a probability tree or things like that, but it's pretty long. So what we're going to do today is a nice quick way to answer those kinds of questions. And as the chapter goes on, they're going to get more complicated. So an introductory thing, or at the root of all of this, is Pascal's triangle. Now this is a very simple thing to construct. Pascal is given credit for that. I assume probably someone else had invented it and found some uses for it as well. So what you do is you start with the first row has a 1, and so does the second row, and every row has a 1 at the outside. The interior numbers are governed by the 2 numbers that are above. So this 2 is a 2 because there's a 1 here and a 1 there, so they add to 2. Similarly, we get 3s here because that's a 1 and a 2, that's a 3, that's a 2 and a 1, and that's a 3. So what I'd like you to do is pause the video and populate the next 2 rows of Pascal's triangle. Okay, let's see how you did. So I end up with 1, 4, 6, 4, 1 on the next row, and then finally on the last row here, 1, 5, 10, 10, 5, 1. Now, we do need to note something. This is considered row 0, the first one, and then we have row 1, row 2, row 3, row 4, and row 5. So these are the row numbers. And the reason we start with 0 will become clear perhaps a little later, or maybe I can explain that in this section here. Okay, let's put Pascal's triangle to work. Now here's a question. Flip a fair coin 5 times. How many ways can we get exactly 2 heads? Now this is one of the steps along the way to figuring out the probability of getting exactly 2 heads. It's one of the steps. So how many ways can we do that? That's kind of hard. You could do this. Head, head, tail, tail, tail. That's one way. Now just to make sure you understand that order is important, that is a separate outcome. This is getting 3 tails first and then 2 heads. So these 2, even though it looks kind of the same, they are different outcomes. And then there's a whole bunch more. We could do tail, head, tail, head, tail. Okay, cool. We're moving right along. But you could probably see that figuring out how many ways to get 2 heads in this method, making a list, it's going to be a little difficult to make sure that you got all of them. You've got to keep track. Did you get every possible way of getting 2 heads and 3 tails? And so that is challenging, whereas using Pascal's triangle is not challenging. So watch this. Row 1, or row 0, is 0 flips. So if we flip a coin 0 times, we're going to get 0 heads, and there's only one way to get that. There's only one possible outcome. There you go. So if you flip a coin 1 time, there is one way to get no heads and one way to get 1 head. That's it. You're either getting a head or a tail. So you only have 2 possible outcomes. Now, if you're flipping a coin twice, you have 1 way to get no heads, you have 2 ways to get 1 head, and you have 1 way to get 2 heads. And so this would be, flipping a coin twice, you'd be tail, tail, that's 1 way. There's only 1 way to do that. To get 1 head, you get head, tails, or tails, heads. So that's the 2 outcomes that get you 1 head. And then here is 1 outcome that gets you 2 heads. So here's the list for flipping a coin twice, and that's on row 2. So you can see as we go down the rows, it's going to tell us how many ways there are to get various combinations. for example, row 4 tells us all the ways that we can, and how many ways we can get certain combinations of heads with 4 flips. 1 way to get 0 heads, 4 ways to get 1 head, 6 ways to get 2 heads, 4 ways to get 3 heads, and 1 way to get 4 heads. So this would be flipping a coin 4 times. So now here we come to our question. Flip a fair coin 5 times. How many ways can we get exactly 2 heads? So go ahead, pause the video, use a triangle, and come back with your answer. Okay, if you did it this way, 5 flips, 1 way to get no heads, 5 ways to get 1 head, and 10 ways to get exactly 2 heads. So there's 10 ways. Now, you're not yet at calculating the probability of getting exactly 2 heads, but this is an important step, and it's part of the formula that we're going to use. Let's take a look at the formula that will do the same thing as Pascal's triangle does for you. Now, the triangle is always something you can generate and use. Most times, this method is quicker, but sometimes you might be struggling to understand how to use the formula. Maybe you forgot it, and you can always go to Pascal's triangle for this. So, check this out. This is a combinatorics notation. We're talking about combinations of things. So this means when you put n over r, it represents the number of ways to choose r items from n total items. So how many ways can we choose r items from n total items? And we have a nice formula for this, and it's not super complicated. N over r is just n factorial, or not, this isn't n over r, this is our combinatorics notation. Nr is going to be n factorial over r factorial times n minus r factorial. Okay, pretty good. Now, let's take a look at our example. We have choosing 2 items, which would be heads, out of 5 items, which is our total coin flip. Now, I realize we're not technically choosing heads, but you could think of it as something where you reach into a bag that you can't see, and there's 1 coin that's all heads and 1 coin that's all tails, and you choose. You choose it 5 different times, and that would be, you could use the word choosing. We're flipping, but same difference. So, check this out. I want you to write this little combinatoric statement with our numbers from there. Pause the video and do that. Okay, how many ways can you choose 2 items from 5 items? Pretty straightforward. Now, populate the formula with these numbers. Okay, here you go. My first step, I did a straight up plug-in. I did my n factorial over my r factorial, and then I did my n minus r in the parentheses factorial. Now, we can simplify that pretty quickly. So this becomes 5 factorial over 2 factorial times 3 factorial. Now, you need to remember what factorials are. And let me just give you the example of, let's say, 4 factorial. 4 factorial is just 4 times 3 times 2 times 1. It's that number. So we've got 4 times 3 is 12, times 2 is 24, times 1 is still 24. So 4 factorial is 24. So that's just an example so that you know what this means and what to do. What I'd like you to do now is pause the video and figure out what this actually ends up being. Congratulations if you got 10, because that's what it is. Now remember from the last board, using Pascal's triangle, that's what we got, was 10. There's 10 ways to pick 2 out of 5, to get 2 heads out of 5 flips. Now I want to show you a couple shortcuts for how to analyze this. You could just figure out what that number is, and then figure out what this number is, and then try to spend some time canceling and dividing, but there's some shortcuts here. So I noticed that I have a 3 factorial on the bottom. So watch this. I can rewrite the top as 5 times 4 times 3 factorial, because that's what's left there, over 2 factorial times 3 factorial. And now I can cancel my 3 factorials. And I have 5 times 4, which is 20, over 2 factorial, which is 2 times 1, which is just 2. So we have 20 over 2, which gives us 10. So you definitely want to be able to cancel like that. Now, your calculator has a factorial function in it. So you could put this into your calculator and it will tell you what that number is. Just remember, if you're in a test that has calculator restrictions, like no calculator, then that's going to be a problem. So I think you should be able to do this algebra by hand. Let's do a little bit of notation here. And the notation takes a little bit of getting used to, but once you've done it enough, it's going to start making sense and you'll just be able to rattle it off when you need to. So, capital X, this is our random variable X. This is just kind of part of the format of the thing. The B here stands for the fact that this random variable follows the binomial distribution. So you're going to get problems that fit that. So, but in the notation we put B, and that allows us to do all of the stuff that we're going to do and use all the formulae that we're going to use. N is the number of trials. Lowercase n is the number of trials, and lowercase p is the probability of success. Okay, so that's a lowercase p, not an uppercase p. When you see that, like, what's the probability of something? That's the uppercase p. Okay? So now we have a notational way to express our overall situation. So I want you to think about what we were doing. We flipped a coin 5 times, flipped 5 times, and we're looking to calculate a probability of 2 successes. So see if you could plug that information in here in some way and express our situation. So pause the video and come back. Okay, check this out. Random variable X follows the binomial distribution. We're doing 5 trials. Remember, we're dealing with a coin, so the probability of success is 1/2 or 0.5. Okay, so on this board, we're going to calculate our probability. We're trying to find the probability of getting exactly 2 heads in 5 coin tosses. So check this out. This is the formula that we're going to use. I'm going to explain that, and then we'll do a plug-in step on it. The probability that random variable X has R successes, remember R from before was the number of successes that we got, is equal to the combinatorics, the N over R, you get that from the Pascal's triangle, or the formula that we did a couple boards ago, times the probability of success, little p, raised to the R power, times 1 minus little p, which this is the probability of failure, by the way. Remember, both these probabilities have to add up to 1, raised to the n minus r power, okay? So you know all your variables now. So what I want you to do is pause the video and do the plug-in step for this calculation. Okay, here we go. Probability, random variable X, we have 2 successes, so 5 coin flips. The X, the random variable X stands for how many heads we get, so success is 2 heads, equals combinatorics 5 over 2 times 1/2 to the 2nd power, that's our R, times 1/2 to the 3rd power, that's our n minus r. And the 1/2s are just the probability of getting heads and the probability of not getting heads. So this is actually a pretty simple one as far as the probabilities go. Okay, so now what I want you to do is pause the video and calculate all the way through until you find out the actual probability of getting exactly 2 heads in 5 coin flips. Okay, check this out, big moment. So I expanded my combinatorics term, 5 factorial over 2 factorial times 3 factorial. And I didn't bother to do all this because we did this 2 boards ago. This ends up being 10. That's that same number from Pascal's triangle. So I brought my 10 down. And then 1/2 squared is 1/4. 1/2 to the 3rd power is 1/8. So multiplying straight through, we have 10 times 1 over 32, which is 10 32s, which works out to be 31.25%. So what that means is if you flip a coin 5 times, it's 31.25% chance that you're going to get exactly 2 heads. Okay, here's a very similar problem, but with a die rather than a coin. So 6 sides, all equally likely. What's the probability that if you roll a die 6 times, you're going to get exactly 3 6s? So pause the video, set that up with a plug-in, and come back. Okay, let's see how you did. So I did my plug-in step here, where I just did my combinatorics term, 1/6, that's the probability of success for rolling a 6 on a 6-sided die, 2, the R power, and then 1 minus 1/6, That's the probability of a failure to the n minus r power. So this ends up being 5/6 to the third. This is 1/6 to the third. I just simplified that way. And I went ahead and did my plug-in step for my factorial. Now, just to evaluate this factorial, we haven't done this one before. I couldn't just grab the 10 from 2 boards back. I went ahead and stretched it out. So I did my 6 factorial, but I stopped at 3 factorial because I know I have 2 3 factorials on the bottom. So I can cancel those out just to make that easier. Now I have a 3 factorial and a 6/4. I can't quite cancel, but here's what I did. I did 6 is 2 times 3, and then my 3 factorial is 3 times 2 times 1. So the 2 and the 3 cancel there, and I have 5 times 4 over 1, or 20. So that is what's going to go here. So if you haven't already done so, pause the video, put that in, and finish this probability calculation. Okay, let's see how you did. Here's my 20 for my combinatorics term for my work over there. Then I've got 1/6 to the third is 1/216. 5/6 all raised to the third power is 125/216. When I multiply through on the tops, I get 2,500. And when I multiply on the bottom, which is just 216 squared, I get 46656. Do my division, and I get 5.36%. Okay, we got there. Now, I always think it's good to do a reality check. We're rolling a die, and we're looking to get 6s. The chance of getting a 6 on one roll is just 1/6. So rolling it 6 times, it's still going to be pretty low odds to get 3 out of 6 6s. So we do our math and we find out that it's only 5.36% of the time that you're actually going to get 3 6s in 6 rolls. It also points out that your intuition about this probability is probably not correct. If it's 1/6 chance to get a 6 on one roll, then why not multiply it by 6 because you got 6 rolls? That would give you a 6/6 probability, or 1, which is certainty, and that ain't true. So this shows you that situations like this that use combinatorics will give you some probabilities that are maybe a little surprising. Here's a tricky kind of a question that you might see. It actually has a fairly simple solution, but it might be hard to see that. So here we are, we're rolling our die 6 times, and we're looking at the probability of 6s, but now it's a little different. What is the probability of at least 1 6? So we get 1 6, 2 6, 3 6, 4 6, 5 6, or 6 6. So you could calculate all of those probabilities and add them up, but oh my God, that's too much. So here is the probability statement, what we're after. That our random variable x is at least greater than or equal to 1 success, that we have at least 1 success. There's another way to state this that's going to make things a whole lot easier. Pause the video. Think about that. It's something about the total probability of every situation. Okay, the total probability of every situation is always 1. So what we can do is we can subtract from 1 the probability of no successes. Okay? At least 1 means we have 1 or more. So really all we need to do is subtract the probability of 0 successes from 1, and we'll have our probability of at least 1. So you have enough with the last 2 or 3 boards to actually do that calculation. So go ahead, pause the video, do that, and come back. Okay, let's see how you got so far. So check this out. I'm doing 1 minus the probability of 0 successes. So the combinatorics terms is 6, 0. And then probability of success is 1 6, but we're raising that to the 0 power. And then probability of failure is 5 6, raising that to the 6th power. This is r, which is 0. This is n minus r, which is 6 minus 0. So that's 6. So now, you've got to take a look at this. This is 6 factorial over 0 factorial times 6 factorial. And this is one of those things you kind of have to remember. You know, the 0 power gives you 1. So anything to the 0 power is 1. 0 factorial is also 1. It's not 0. So you don't have a divide by 0 problem there. You just have 1 times 6 factorial underneath 6 factorial. So that also becomes 1. So we have 1 minus 1 times 1. So those are going to go away. That's just 1 times whatever this fraction is. So go ahead, pause the video, finish that out, make sure you got your answer, and come right back. Okay, finished crunching my numbers, did this, I got 0.3349, subtracted that from 1, and I get 66.5%. So that's the probability of getting at least 1 6 in 6 rolls of a die. So I don't think that's necessarily a very intuitive answer. I would think there's probably a higher probability of that. But this is how this works out. This is the math of it. Math doesn't... Okay, let's quickly wrap this up. There are a few requirements to do this whole process we've been doing in this lesson. And they are, we need a fixed number of trials. We can't just have 5 trials, 6 trials, 2 trials, 3 trials. We need to analyze the situation with the same number of trials to compare probabilities. Second thing, each trial has 2 possible outcomes. So with a coin, that's pretty obvious. You get heads or tails. With a die, that's not so obvious because technically a die has 6 possible outcomes. But if you're measuring the probability of getting 6s, your 2 outcomes are 6 and not 6. So don't get pulled in to having more than 2 outcomes. To do this, you need only 2. The probability of success has to be constant. It can't change. And finally, each trial is independent of the other trial. So I want to illustrate these two. They're kind of very similar. With a die, if we roll a die, the probability of a 6 is the same for every single roll. They're independent of each other. However, if we take a deck of cards and we're tracking red or black, and we pull a card, and then we don't put it back, no replacement, the next draw probability is going to be a little different depending on what card we drew the first time. So 2 things are violated there. The second draw is not independent of the first, and the probability is not constant. If I drew 1 red first, now the probability of getting another red is 25 out of 51 instead of 26 out of 52. And it's a small difference, but it is a difference. So you can't do this analysis that way. If you put the cards back every time, that's different. Then you could do that analysis.
Now that you've watched the video, take a moment to write down any remaining questions so you can bring them to our next class. Also, remember that you can come back to this video, watch it again if you want to deepen your understanding or fill in any gaps. Lastly, if you enjoyed yourself, please click like or subscribe.